Alright, welcome everybody to our review of stoichiometry. Okay, to review stoichiometry real quick, we're going to have to actually go back to our mole map because our mole map, stoichiometry relies very heavily on that. So for our mole map here, we have to remember a couple different things. Okay, first thing we need to remember is that what we're converting to. Alright, where we're going to convert. So if we start at moles, so if our quantity that we know is at moles, and we're going to grams, we have to remember to go from mole to grams or grams to moles, we need to go to the periodic table, okay, to find the molar mass of whatever we're trying to find. If we're looking at volume, okay, if we're going from moles to volume, we need to convert by a factor of 22.4 liters. If we're going from moles to atoms and molecules, okay, we need to use our number, what the number is for moles. So we're going to convert by 6.02 times 10 to the 23rd. Okay. Now, this works really well if we're just converting with one substance. Okay, so I'm going to label this substance 1. But if we have a problem ever where we need to convert from one substance to the other, we're going to need just a little bit more overall. So that's why we need to basically double this now. And this is our expanded mole map. Okay, so now we're going to be talking about two substances, substance 1 and substance 2. Okay, so once again we're going to the periodic table. Nothing's changed about it, we're just copying it down real quick. Okay, now if we're going from one substance to another, okay, if we're going from substance 1 to substance 2, we have to get it into moles first to be able to convert it, whichever way we're going. Okay, and we need to convert by what we call the mole-to-mole ratio. And the mole-to-mole ratio basically is, if I have so much of this, I need so much of this in turn. Okay, so if we're thinking of water, we've got 2H2O, we can say that decomposes to 2H2 plus O2. Alright, this is a balanced equation. We need to make sure it's balanced before we start that, but we can say for every 2 moles of water, which is what this is right here, 2 moles of water that decompose, we get 1 mole of oxygen. For every 2 moles of water that we can decompose, we get 2 moles of hydrogen. That's our mole-to-mole ratio, and we use that to convert. Alright, so here we've got our mole map. Okay, let's go ahead and try a couple problems. Alright, so carbon disulfide is an important industrial solvent. It is prepared by the reaction of coke, which is just simply carbon, with sulfur dioxide. And here's the equation here. 5C plus 2SO2 produces CS2 plus 4 carbon monoxide. So the question is, how many moles of carbon are needed to react with 5.44 moles of SO2? Okay, so it's asking for how many moles, and our given is our 5.4 moles right here. Okay, so let's go ahead and start this. We're going to use dimensional analysis to solve this. Alright, so let's think. 5.44 moles of SO2. Now, I can't stress this enough. Labels are so important in this chapter. If you're not labeling, you're in trouble. Okay, but 5.44 moles of SO2. That's what we start off with. Okay, so let's think here. Let's go back to our mole map real quick. If we're in moles of substance 1, we need to know the mole-to-mole ratio to get to substance 2. Okay, so let's go back there. We've got 5.44 moles of SO2. So, let's think of our mole-to-mole ratio and cancel accordingly. So we've got moles of SO2. So we know moles of SO2 needs to go on bottom. Let's look. For every 2 moles of SO2, we need, what are we trying to convert into? We're trying to convert into carbon. We need 5 moles of carbon. Okay, we get that from right up here. For every 2 moles of SO2, we need 5 moles of carbon. Okay, and what is it asking? Just moles of carbon, so we're good right here. So we could get out our calculator now. 5.44 times 5 divided by 2, and that equals 13.6. So we have 13.6 moles of carbon are needed to react? Okay, that was a pretty simple one there. So let's try another one. Alright, the reaction of fluorine with ammonia produces dinitrogen tetrafluoride and hydrogen fluoride. Okay, with the equation right here. If you have 66 grams of NH3, how many grams of F2 are required for complete reaction? Okay, so let's think. What is this whole problem asking here? It's saying we have 66 grams of this. So this is our known. And it's asking how many grams of fluorine we need. Fluorine that we need. Okay, so we start with what we know. So 66.6 grams of NH3. That's our beginning quantity here. 66.6 grams. So let's look at our mole map. Where are we? Okay, we are in grams of substance 1 here. That's where we are. We're in grams of substance 1. So that means we have to convert to moles first before we can convert to our second substance. Okay, so that means we need to go to the periodic table for this. Alright, we need to go to the periodic table. Well, hold on one sec. So let's set it up. So we need grams of NH3. Okay, for every 1 mole of NH3, we need so many grams. Well, how many grams is this? Okay, so to do this, to calculate grams, we need to do a little side equation here. Let's think. Nitrogen is 14.01 grams. Okay, and hydrogen is 1.01, so 1.01, and there's 3 of them, so times 3. So let's add all that up. Okay, 14.01 plus 3.03 equals 17.04. We have 17.04. So in 1 mole of NH3, we have 17.04 grams of NH3. So now the grams of NH3 is canceled. Okay, so now that we're in moles, we look back at our mole map. We're in moles of substance 1. Okay, we're in moles of substance 1. We need to go to moles of substance 2, so that means we're going to do our mole-to-mole ratio. Okay, so to do our mole-to-mole ratio, so we're going from NH3 to F2. So for every 2 moles, we get this right here, 2 moles NH3, we have 5 moles of F2. Okay, 5 moles of F2. So moles NH3 cancels. Now let's see where we are now. Okay, so we're in moles. What is it asking for? How many grams of F2? So let's go back to our mole map again. Okay, we're in moles, okay, of substance 2. We need to go to grams of substance 2, so that means we need to go to the periodic table. Alright. Okay, so let's get this set up before we actually go to the periodic table. So for every 1 mole of F2, that means this cancels out now, we have so many grams of F2. So that's where we go to the periodic table. Fluorine is right here, 18.99 or 19 even. Okay, so be 19 grams, but wait, this is a diatomic molecule, F2, so 19 times 2. What is that? 19 times 2 should be 38, right? Yes, it is. Okay, 38 grams of F2. So now we go through where everything's canceled out. We just plug it all into our calculator now. Okay, so we've got 66.6 divided by 17.04 times 5 divided by 2 times 38, and that equals 371. Okay, and with sig figs it just comes out to 371. Alright, so for this we need 371 grams of F2. Okay? Alright, that's our second problem. Do we have enough time to do another one? Oh yeah, you bet we do. Okay, so here's our third one. How many molecules of oxygen are produced when 29.2 grams of water is decomposed by electrolysis according to this balanced equation? Alright, so let's see if we don't necessarily need our mole map here. Okay, so to start off, we have 29.2 grams of this, 29.2 grams of water, and how many molecules of oxygen. So we're wanting to know molecules of oxygen are produced. Alright, so here we go. And 29.2 grams of H2O. Okay, so for every 1 mole of H2O, we need 18.02 grams of H2O. Okay, so now grams of H2O is canceled. We're in moles, so that means we use our mole-to-mole ratio. Go back to your mole map if you need confirmation on that. So mole-to-mole ratio for every 2 moles of water, moles of H2O, we produce 1 mole of O2. Okay, so that's moles of H2O is canceled now. Are we done yet though? No, because it's asking for how many molecules. So for every 1 mole of O2, okay, we're going to have 6.02 times 10 to the 23rd molecules. Okay, so now we're ready to use our calculator. So 29.2 divided by 18.02 divided by 2 times 6.02 times 10 to the 23rd equals 4.88 times 10 to the 23rd. 4.88 times 10 to the 23rd molecules of O2. Alright, so there's a quick little review on stoichiometry. The key to stoichiometry is keeping track of what substance we are in. Okay, if we're in substance 1, substance 2, where we're going. If we need to go from volume to grams, okay, we have to go from volume to moles, mole-to-mole ratio, and then once we're in moles of substance 2, then we can go up to grams. Okay, each time converting by what our mole map indicates. Hopefully this makes a little sense. If not, please come in and get some help. Hope this all works for you. Have a good day. Bye.